I'm recording now, y'all. Sorry. So VLOOKUP, and our first value, the lookup value is the ID. Then we have to press comma, and we want to pick our table array, which is in sheet 2, where we've now got our summary, pivot table with all of the count of the classifications of works. So then we select column A because that's where the ID is. If the ID was actually in column B, we would select column B and drag to what we want to bring over. But instead, we're going to select A because that's where the ID is, and we're going to drag all the way to the end. Now you'll notice as you drag, it tells you how many columns you're including in this selection. And right here above this this little cross, right here above my mouse right now, you can probably see it says a lot of rows, like over 1 million, R, which means rows, and then it says by 34 columns. Okay, that means I've selected 34 columns. So I let go because I've got it all selected, and I hit comma, and then it asks me for a column index number. That column index number is the column that I want to return the value for over in my other sheet. And so I want to return the grand total, right? I want to return the total number of works. So that is column C, but Excel doesn't want to know column C, it wants to know an account. So we have 34 total columns. It wants to know essentially the third column is what it's going to return. So I type 3, and then I press comma again, and it wants to know if I want to make an approximate match or an exact match with the ID. Well, I know I want to make an exact match because I don't want it to approximate this. So I double click false, and then I hit enter. And so now it's telling me that Robert Arneson has 2 works in the Met. I drag it down, and Cristobal has 1. So it's matching ID to ID. On the third column, it's bringing in the value so that we see how many works of art we have. So now remember, I want to bring in the number of works for each classification. All you have to do is highlight the formula, right click and copy, or Control C and copy, go to the next column and paste the formula, and then paste the formula, paste the formula, paste the formula, paste the formula. Here's the difference. So we've got architectural model, sorry, and then architecture, audio, etc. What we need to do is we need to change that column index number because it's still looking at total works. We come over here and I say, okay, architectural model is column 4, architecture is 5, audio is 6, collage 7, etc. Right? So now we know that those are the numbers, and you may have seen it pop up, right? Column 1, 2, 3, 4, 5. All I have to do is come through here and say, okay, architectural model again is column 4. So change that to 4. Change the next one to 5. Next one to 6. Next one to 7. Next one to 8. And you can select all of those. If this, once we get done, if you do all of them, select them all, highlight them all, and then double click this bottom right corner, and it populates everything. So once again, Cristobal has 1 total work, and it's a design work. And now we have connected all of this works of art by creating a pivot table and then creating a VLOOKUP function. And we've got our massive data set that's usable and ready to work with and ready to visualize. Aren't you glad I recorded that?
I'm going to be super nerdy and ask if, can you send us the original one so I can try that? Okay, thanks.
I'll send you the link to I'll send you the link to the original one so you know
Okay.
where it is too.
Yeah, thank
In
you.
fact, yeah, no worries. I love this data set. So now that you see how I prepared it for y'all to use, um, try it out. Try it out because this is a skill that you don't necessarily ever need to know until you need to know it. And if you know how to do it, it makes your life so much easier, especially when you're using different types of data, tables, data sets, etc. Laura Beth, did you say you've seen people doing HR? Was it you, Kara, or who? Someone said that,
Yeah, that
right?
was me. Yeah.
Yeah. Yeah, so oftentimes with like things like HR, I mean, you've got a person's name, demographics, all that kind of stuff over here. You might have their salary, their job title, their hours, all that in something else. I mean, think about the opportunities you have to now bring data together that's not naturally in the same place. So okay. So that was a nice little diversion into the world of how Eric made your data set. So it did take a minute, but I think it was completely worth it because this is a fun little exercise. I thought. Feel free to laugh or thumbs down or whatever you want to react. But what about the actual visualization? What about the visualization? Did you find it was easy to write about something that you visualized? Was it easy to describe it, right, to your colleagues, professional, family, friends, etc.?
I think for me, it was certainly more straightforward. Like the bar charts are a lot easier for me to get to the point with than the line graphs we were working with the previous weeks. So it felt quicker. I definitely used less words, and maybe that means there was less information to share, but that was just my observation.
Okay. What about others?
I'm actually considering now if I described the visuals or if I simply discussed the data. And I'm not sure.
I mean, yeah. It's okay. It's okay. Sometimes it's hard to describe something that you think is easily consumed, right?
Mhm.
Right. So I understand that. Did anybody, like Laura Beth mentioned, like, the bar charts seem more simplified. Did anybody start? Okay. So I gotta tell you another secret. I don't like, sometimes I don't explain things to my spouse. I actually just make a chart and give it to her. For example, in case you don't know, I'm already like insanely obsessive about data. I go through every month, same day every month, and I summarize our financial footprint, right? How much do we have in savings? How much do we owe on the house? How much do we have in equity in our home? All this kind of stuff, like our stocks, our bonds, our investments, our retirement, and I make a visual for her, and I hand it to her, or I take a picture of my phone and I text it to her. She's at work, and she usually just sends me your typical like emoji response. But that's just how, I mean, we're a family. We're trying to make sure like we are both accountable for our spending, and so this is just one way that we do it. However, she's told me a few times, she's like, I feel like you've gotten really lazy in your description of a lot of things because you can just send me a chart and I'll read it. Hope as you start to use more and more visualizations, dashboards, charts, don't let them necessarily always tell the story for you, because people do misinterpret them still, right? We talked about that a little bit last time. The last thing, I can't wait to, by the way, I haven't reviewed this exercise yet, but I had, of course, your tests are done. But I can't wait to see your bad charts. Did anybody just cringe at making a bad chart?
I think like my Instagram was obviously bad, so my bad chart was more bad than that.
I gotcha. I gotcha. Yeah, histograms are sometimes not very easy to read, but yeah. Did anybody make a really, really like ugly chart that they wanted to talk about?
I put a nice texture on one of my bars, and just one of them.
Oh, you did what, Laura? Sorry, kind of broke up.
I put a texture on one of the bars, and just one
Gotcha.
of the bars, so it's like standing out and terrible.
Fun. I have seen some really bad charts. Did making a bad chart like forcing you to think about like, well, what does a bad chart look like? Did that actually help you remember how to make a good chart? Because you're thinking, oh, I can't do that because that would make it better. Make sense? Cool. Well, good. Well, hey, you've made it through the first test, as well as a good portion of our assignments. I think this is week 6 now. So if you have any questions or concerns so far, please don't hesitate to reach out, ask me. I just want to make sure you know I'm available. But I appreciate y'all. All the work that y'all are doing. I'm really pleased with it so far. I think since we did talk about the exam as well as the assignment, let's go ahead and take that break that we would normally take. Is that okay with y'all? We're about a little over an hour in. Let me refill on my bed and say hello to my spouse. But when we come back, what we're going to talk about is really statistical bias. Okay, statistical bias is really what we mean by meeting or not meeting our assumptions, right? And I'll explain much further into that what we mean by it. But this is sometimes often overlooked in the more applied world, but it's still an important discussion for us to have because I don't want you to think that if you have a statistically significant outcome that is necessarily always going to be true. Like we're always going to have error in our data. So we need to make sure that we can explain it, understand it, and at least, account for it when we can. So let's take, how does 15 minutes sound? Okay, we will come back at 20 after. See y'all then. All right, everybody, welcome back. All right, let's see. Okay, so if we think about all the assumptions that we make in a given day, please don't stress out about this. I apologize if I create any stress in your life, but our assumption when we go grocery shopping is that we're gonna pay for groceries like we did in our data set for the test, and take them home, give them to people who need them, donate them, whatever. But you go grocery shopping, you get what you hopefully get what you need, and then you're done. What if instead of going grocery shopping and getting what you need, you got arrested for, I don't know, going over the speed limit or shoplifting? I've actually seen a guy get arrested at a grocery store because he was trying to steal meat. And this is like a couple of years ago. But we also make many assumptions that we're going to get up and start our vehicles and drive to work or school or anything like that. We make a lot of assumptions, and we always kind of mentally cross our fingers that we're going to meet those assumptions, right? For work, our assumption is that we're going to maintain our employment, right? But if we make bad decisions or aren't productive, etc., then we don't meet the assumptions that are expected of us, and we might see possible termination. Similarly, as in life, we have statistical tests, right? And we run these statistical tests on our data, and if we meet certain assumptions, then that gives us confidence, higher confidence, that our results reflect either a population or the broader sample or the entire data, the entire result. If we don't meet those assumptions, then we aren't as confident, and we might have results that, even while they might be good results, they may not be the most accurate, or they may not reflect reality. So that's kind of what I mean by assumptions, right? We have to make some assumptions, or at least be confident in our assumptions, in order to ensure that we're going to make it to work, because our car is not going to break down. So in terms of you applying assumptions to statistical tests, the majority of what we're going to look at here is based on what we call a linear model. And Andy Field discusses the linear model extensively in the chapters. And what we mean is that a model of data with predictor variables and outcome variables, dependent, independent, that sort of thing, we assume that our model follows some sort of linear pattern, right? And so the assumptions that we make are essentially that, hey, guess what? There's a linear relationship. The older you get, the more likely you are to pass away, right? The more money you have, the lower your happiness, right? Higher income, lower happiness. All of these things are tested constantly. But we often think about the linearity of specific outcomes, and thus we have to meet some assumptions in order to know that our model is accurate. So here, I don't know if y'all have followed the cryptocurrency craze that's been happening in our world for about 5 years or so now. But remember how we did this last week? We looked at line charts, and I said, you can add a trend line, and you can add the R-square value, which is the proportion of variance that's explained by this linear model. Remember that? Kind of, sort of. You took a test in the meantime, so I don't blame you. But if you look at the price of Bitcoin, which really just was insane last year. I've run it for February of 20 through February of 21. It went from about 10,000 a share or 10,000 a coin, all the way up to roughly 60 grand. That's almost a 600% increase, right? So if we look at that using a linear model, we're like, okay, that kind of follows a linear pattern, right? As time goes by, the price of Bitcoin goes up. But it's a false assumption because we know that's not a linear pattern, right? That's actually not a linear pattern at all. It's much more of what we call a logarithmic pattern. And so this logarithmic pattern, if you apply this kind of a model to it, understanding that the price actually goes up at a greater rate over time than the times before it, then you actually can, it fits it pretty well. This is what we call the model fit, is this R squared. So it fits about 87% of the variance. So not everything we measure is linear in nature, but for the purposes of this class, we're going to utilize a linear model for measuring statistical results, predicting the future, those sorts of things. So when we talk about outcomes, what we want to think about are whether or not the outcome is additive or not. And what that means is that the predictor itself changes based on the independent effects of other predictors, right? So the change in an outcome is affected independently by other predictors, right? And that's an assumption we make. We know it's not always true, because I promise if you didn't sleep well last night, you might not have also eaten very healthy today, right? Anybody agree? I know I didn't sleep well last night, and I gorged myself on a bag of combos coming back from one of our universities. It was a 2-hour trip there and back. I went and did a guest lecture for a data journalism class. And on the way back, I was like, I'm starving, I'm tired, give me the cheese. So, but nonetheless, this idea of having an additive type relationship is that, essentially these changes are independent of changes in other predictors, right? So studying, sleeping, eating, all of those have been known to be somewhat predictors of a standardized test score, like an SAT or an ACT score for high schoolers. Not only, when you control for things like their prior high school coursework and their GPA, the night before, how much they sleep, as well as having a good, healthy meal, and even studying up through the week prior before the exam, all of those are additive in some way because they independently affect ACT, right? Oftentimes we create linear variables that aren't just one predictor on one outcome, right? How often do we find one predictor that can predict 100% of the outcome? Is there ever really a situation like that? I was asked by a former student, what's the most predicted thing you've ever done? And I told them probably proposing, right? Proposing to my wife. I knew she was going to say yes, 100%. And they pushed back on that. They were like, "Are you sure?" And I said, "Yeah." And they're like, "Well, what if it was raining that day?" Because I proposed outside. And I said, "Well, I'm pretty sure I wouldn't have proposed." And they said, "Well, then she wouldn't have said yes that day, right?" So there's lots of factors in our world, and while we might think that something is caused by one outcome, we really need to be more open and understanding that there's lots of factors at play, right? So sleep, study, and also having a full belly are all seen as these independent predictors of ACT, and it's a linear relationship, right? It doesn't necessarily have a logarithmic shape to it. The more you sleep and the more you study, we find this to be fairly linear. Now, in terms of the outcomes itself, when we talk about normality, you've learned about normal distributions already, but I want you to think about not necessarily the outcome variables, but rather the normal distribution of what we call the error values, right? So if we have an average score, but we know the true score is, maybe a point or two away from the average, well, then we've got a lot of error mixed in. So when we try to distribute our values or our error values, we might find that those errors are concentrated for different reasons, for different types of predictors. I don't know if you can see the screen. I'm sorry for the small text here, but when you look at a sample of people, like for happiness, and this comes straight out of the book. When you study someone's an entire population and their ratings of happiness, you find that there might be like these two different segments, right? A large population or proportion of the population rate their happiness at a 10, and another large portion rate at like a 17. However, what you find there is the true mean may be in the middle, but when you look at the error values, right, you actually find them to be distributed separately. So what we found here is that when you look at the predictors as to whether or not the population is a human versus a Muppet, and that, again, this is example data, right? But when you actually look at the distribution of your data and find that there are certain categories that predict either lower happiness, of course, the humans, right? Because Muppet, I don't know if anybody watched the Muppets growing up. I kind of came in at the tail end of the Muppets, but Muppets were like the happiest things in the whole wide world, unless that big angry guy came down to their lair. Sorry, I'm dating myself. But nonetheless, we find that these kinds of predictors we're able to see kind of the variation in the scores and the error values by understanding kind of the normality of our data. So when we talk about whether or not something is a significant predictor of a particular outcome, we're really talking about this sampling distribution. And it's typically assumed to be normal, right? We know, however, in reality, most of our distributions are not normal. For example, let's imagine this distribution is hours of sleep. Hours of sleep. What do you think these two concentrations would be? Take out happiness. Don't ignore the word happiness. What do you think these two categories are, where you see a high concentration in the low amount of sleep and a high concentration in the high amount of sleep? What do you think could be skewing that data in our distribution? And it's not humans or Muppets. Could it possibly be age? Like less than 5 years old? Greater than 5 years old? Or rather, I'm sorry, less than 5 years old on the high end, greater than 5 years old on the low end. Kara, do you want to chime in?
I was going to say, just based on what Manta just said, it could be the presence of children.
She's the one who gave me the example. I thought y'all would catch on really quickly. So I read that and I was like, that's actually a really good example. If the way, but think about it. What if we tried to look at the distribution of our outcomes and saw that the errors were, not normally maybe they naturally were altogether normally distributed, but when we look at two separate groups, we see that they diverge, right? And I hear that kids sleep a lot. I don't know, Manta, you tell us, but not so much. Okay. Another term so that's how we think about normality, right? We have to understand normality, but in order to have predictors, we have to have differences in the distributions of those scores for the separate groups, separate predictors, right? When we think about what we call homoscedasticity, say that out loud with me all at once. Everybody on mute. Ready? 1, 2. Waiting on you, Laura.
Okay.
3. Homoscedasticity.
Homoscedasticity.
This is the best audio clip of the entire course, by the way. It's never fails. Everybody's like 5 seconds off. But yeah, homoscedasticity. What we mean is that the variation should be stable. So if we see variance at maybe for hours of sleep, for example, we'll go back here. If we know there's going to be variation, right? Some babies sleep less, some babies sleep more, some adults sleep less, some adults sleep more. What we assume with homoscedasticity is at least the error values aren't extremely different for different groups or different settings, that they're all somewhat stable or somewhat reliable, right? So the example in the book is looking at the concert venues, right? So Andy Field went to a bunch of concerts over in England and Ireland. So you've got Cardiff, Dublin, and what he found was that for different, I think it's for different performers, the ringing in the ears, right, was basically the same. If you went to see, I don't know, who's everybody's favorite on this class? Who's your favorite artist? Your favorite music artist?
Usher.
You said Kesha, Leah?
I said Usher.
Usher. Oh, okay. Sorry, I thought you said Kesha. Kesha's my favorite too. No, I'm joking. So Usher, yeah. So Usher, if you performed at each of these venues, we would assume the average ringing in the ears to be somewhat stable, right? It's the same performer, right? But what if we had, and this is what we call homogeneous, variation. It's the same, regardless of the venue. We can get the same result. It's also a measure of, a little bit like we think about reliability, right? When we think about the heterogeneous, right, not homoscedasticity, but the heterogeneous effect would mean that, well, people reported ringing in their ears at a much wider variance at these different types of venues. So maybe when you go to Newcastle and you go see an Usher concert, and maybe the acoustics are just really bad, right? Maybe there's not a lot of cushion, to really kind of cushion the noise, and everybody doesn't. It's affecting different people in different ways. Lord Beth, what were you saying about the last city?
About the last phase?
I'm sorry. I read your text in the chat. It said I missed the last city.
Oh, in the skedasticity or whatever. I missed whatever the last city.
Yeah, there you go. It's it's a very populous area, homoscedasticity. That's fine. So when we see this kind of variation differences, it violates another assumption. So all of these are different types of assumptions that we make about our data. We want to make sure that our variance is somewhat stable, right? We want to make sure that our error values are also somewhat normal, right? And that way we can ensure that at least our outcomes are similar. When we talk about our actual observations, we want to make sure that we don't see a lot of overlap. So ignore the very, very, very low. Understand that I did this just to kind of show you. Amazon, while there has been fluctuation, Amazon has not fluctuated over the same time period nearly as much as Bitcoin has, right? To use the same example from last time. What this means is that, well, if we were trying to predict things, if we were trying to test a linear model on stocks, for example, we could assume that Amazon's price fluctuations don't necessarily correlate with Bitcoin's price fluctuations. This is called an independence of observations, right? If Amazon went up $1 a share and Bitcoin went up $1 a coin on the same day, and every day they matched, well, then we would probably have to assume that there may be a relationship between how Amazon fluctuates and how Bitcoin fluctuates. One of the things that I like stocks, by the way. I dig around the stock market a lot, and I've noticed something. I don't know if anybody else here is like a day trader mindset or anything like that. I'm not that person. But oftentimes the market overall will shift and affect all stocks in kind of the same way, even though there may not be a justifiable explanation for it. So oftentimes, if, let's just say, Delta Airlines changes to go up, it may not be really anything related to Delta, but it might be overall the market is doing better and there's more confidence in prices. So don't think that stocks are always going to be independent of each other, but at least in this case, it's insane how much this whole idea of cryptocurrency kind of separated itself from the more established financial markets, right? And you can, feel free to look up this kind of historical data for all of them. Anyway, just wanted to make that point. So remember the box plot that I showed you how to make last week? Remember I told you if you have a box plot and it comes with these like little like extra dots on the end, those are typically what Excel identifies as outliers. And I use Microsoft Excel for this. Those may or may not be true outliers, but at least it identifies them as extreme cases in comparison to the rest of the distribution of the data. So pop quiz, and by the way, hint at your next test, what's this middle line for? The middle line right here.
That's the mean.
It's the what?
The mean.
How many syllables is in that word, Kara? Sorry, you're kind of cutting out.
Oh, just one.
Just one syllable. Okay. No, you're close. Add 3 more
Isn't
syllables.
the X the mean?
Yeah.
Yeah.
What about the X is the mean?
middle
So what's the line?
is
The
can you
middle
put
line
it?
is the median.
Yeah.
Yeah. Think about it like that. Think about it like middle of the highway is the median, right? So the middle line is the median. Good job, Will. Yeah, the X is the average. I've included all of the values just as the way of showing you kind of where they place. What is this top bar right here?
The max.
Is that the max? Oh.
It's the max if we consider these to be outliers, right? So in this darker yellow box, it is the true maximum, right? What is this bottom line then? Over here in the middle, the wider, I guess like the off yellow.
The minimum?
The minimum, right? Again, we have these outliers in the darker yellow one. And then the bottom of the box right here.
The 25 percentile?
That's right. Top of the box, not Rod Tanay. No, you're good. You're good. I just want everybody else to chime in too. Top of the box.
The 75th percentile mark.
That's right. That's right. Okay. So good review, good recap. Again, hint, hint, nudge, nudge. These are how Excel identifies extreme cases. But we have other ways of identifying whether or not there are outliers in our data. So in SPSS, we can use what's called a PP plot, a P-P plot, and this looks at essentially calculating z-scores and comparing those z-scores back to the actual score, right? Looking at z-scores for all of your values and then comparing them to see what the differences are. So in this top histogram, right, this top left one, even though there's a little bit of a dip in the distribution, it still overall has somewhat of a normal distribution, right? It's kind of a more balanced distribution. Notice that the P-P plot, I hate saying PP, feel like I have to go to the bathroom. But the P-P plot, notice how close all the marks are, or all the values are to this diagonal line. When you have all of those marks, trying to get my arms right, when you have all those marks very tightly knit on that diagonal line, it means you probably don't have any outliers. It's one way of visualizing them, right? However, if you notice that you start to see some space between this diagonal and the overall distribution of values along that line, then more than likely your data are being influenced by some outliers here. And then down here at the bottom, you see a little bit bigger, right? You have a couple of outliers. What kind of skewness do we see on these bottom two charts, y'all?
Positive.
Positive, that's right. So positive skewness, it may or may not imply it always, but we do see that we have some possible outliers here, right? So this is a good time to maybe tell you, what do you do about those darn things, right? Oftentimes the case for me, as in my day job, is our outliers are probably related to miscoding. So if I have a student that's 150 years old, that's fantastic if it's true, but more often than not, it's false, right? So all I have to do is go in and correct it. We have human error all the time. However, if let's just say we have a distribution of ages from about 18 to 60, and then we truly have a 90-year-old person that wants to take a course. Well, if we're really trying to look at predictive power, and we understand that 90-year-old person's probably going to influence the mean, right? And may or may not influence the outcome, but they're as a predictor, they are probably going to influence, the other set of predictors. You can trim it, but what I try to do is always evaluate if I take it out. Am I changing the very nature of the data set, right? And so if I can take it out and I won't have any effect on the average, on the standard deviation, some of those other things, then trim it, right? Take it off. Or if you have a lot of outliers, sometimes you have more outliers than just one. You really have to kind of think through it. The other way that we've typically worked with this in research studies is substituting that outlier with the highest value that's not an outlier. So coming back to our box plot, you see these two outliers right here. Instead of, if we didn't want to take them out of the data set, because maybe we're asking about attitudes about safety on campus, right? And these students are younger maybe than, I don't know, others, maybe they're 17 years old. And then that's classified as an outlier. Well, then we're probably going to have students a little bit older than them. Instead of taking out their perspective, because it's an important perspective to have, we could move their age or change their age to the next value that's not an outlier. So actually changing it to the minimum, or on the reverse side, changing it to the max. It still is including it in the data set, but it doesn't have as much of an impact on the predictive power of age, right? So there are ways to get around outliers, but typically the two ways that most people deal with them are either removing them or substituting their value. Does anybody have any questions about outliers? Has anybody dealt with outliers in your own work or your own studies? Let me ask you this. When you looked at the data set with political contributions, do you remember that one? Were there any outliers, like really, really high donations, one-time donations? It's okay if you didn't check for them. We weren't there yet.
I just remember all the really low donations. They were like $2.17.
Hey, that was the. Thanks, Carrie. You just brought me back to college. That was my hourly wage as a waiter. and I saw that too. Yeah. So political campaigns have gotten really smart. They know it's easier to ask for multiple small donation amounts, like $5 here, $5 there, than it is to ask someone to like donate $1,000 tomorrow, right? And hope for that one-time donation. In fact, we've started to see this in marketing materials. I've got a colleague who does a lot of data analysis. He does it for free because he enjoys it. He just likes to put stuff together. But at the very bottom of his little email, it says, buy me a coffee. And if you click it, it's like $4 or something. But yeah, so if you want to go back and look at those political donations, look at it with a different lens of how are my data distributed and do we have any outliers, right? Because honestly, that can make or break an outcome, right? If we make the assumption that there are not outliers, but there are, then we really are kind of, taking it a little bit, making assumptions we probably shouldn't make. So it's important to understand the distribution of your data before, in order to identify these kinds of things. But also try out the PP plot and SPSS. I don't think that's part of your homework assignment this week. This week is just a discussion, but go ahead and get in SPSS and play around with it. Feel free to use some makeup data. You can always make up data, and that you can better understand what those PP plots mean. So this week's assignment is just a discussion, but it is a little different. What I want you to do, instead of focusing on purely like the test, like the measures of central tendency like we did before with that article, I want you to go try to find data or a report, rather journal article, that looks at using either correlation, regression, or linear modeling. This is kind of the area where we tend to see people having to test for these assumptions within the linear model. And so first things first, for the sake of everybody, summarize the study in 50 words or less, okay? A paragraph or two. Make sense? Just do a quick summary. Then I want you to describe how the authors checked for these assumptions, whether or not they met the assumption of linearity, normality, homoscedasticity, or independence of observations. Look for all four. Tell us if any or all or some, none, whatever, were actually discussed in your article. And by the way, I'm not going to tell you what article to do. I'd like for it to be more recent, so it's more relevant. But pick an area of your own interest, okay? And you don't need to respond to a classmate this week, but I want you to read, at least come back, around the time that they're due, come back and read through everybody else's, because one of the ways that we broaden our ability to describe and understand all different types of data analysis is to have a more broad perspective, expand our horizons a little bit, and see how people. Ratane, what's your area of interest whenever you look for research articles?
Can you repeat that?
Yeah, what's an area of interest for you if you had to find a research article?
Usually, I told you I like reading business articles or like things on the stock
Yeah.
market and stuff. Is like current news.
Sure. Yeah. So the way that a research article related back to the stock market may write up their results and discuss how they met certain assumptions might differ from a psychology article, right? It might differ from something that's looking at weather phenomena, right? It might differ from me, who's one day going to write an article about the collection in the Met, by the way. One day. I can dream. Which, by the way, did anybody notice how few how few females are in the Met?
Yes, I noticed it.
That I forgot to get into that kind of result and discussion with y'all. But that's one of the reasons why I wanted you to analyze that data, because we see so many museums are still so heavily represented by only a few, like very, very small proportions of the overall population nowadays. I went to this museum in New Orleans, and they are dedicated to Southern arts, only from Southern states, basically from Texas and Oklahoma east, and as far north, I think, as Virginia. But that museum, it's called the Ogden Museum, Ogden. That museum had a fantastic exhibition, and part of the exhibition was actually to add to their permanent collection of a much more diverse audience, right, of artists and the artworks. So that kind of gave me the inspiration to do that exercise for y'all. Because as I was going through it, I was like, I wonder how many other museums are really being proactive and finding art and sharing that kind of stuff. So anyway, sorry, a little off topic, but this, now when you go through and you read about this, it's going to be good for you to understand really, did they meet it or not, and if they didn't, what did they do about it, right? Did it stop them from pursuing a certain part of the study? Were they able to account for it in other ways? How did they handle those sorts of things? So please read through everybody's. We're going to come back at the beginning of the next class and talk about them. But I wanted to kind of go through this kind of brief introduction to these kinds of assumptions, because moving forward, we're going to be looking at different types of tests and making sure that we can account for or explain whether or not we meet these assumptions in our future analysis. Okay? Anybody have any questions? All right. Well, I apologize again for the traffic delay. Thank you for I guess everybody saw their email, or at least maybe logged in early and saw that I wasn't here. I apologize for that. I got back from Jonesboro pretty late and then had to turn right around and come home. So if you have any questions about this assignment, feel free to reach out. And remember, our office hours are there. So let me know if you need to touch base on anything. I'm sorry I did not get a chance. My parents are coming up this weekend. My spouse is getting everything. She was upstairs trying to get we call it the mother-in-law suite ready, and I ended up helping her. So I'm going to stay here and get your exercise, or sorry, your exam results opened up for you. Okay. Cool. I didn't forget about you. And thank you all. Thank you all for being here. And I hope you have a great rest of the week. And hopefully you don't get any bad weather. We've got some rain coming, but stay safe out there, okay?
Thank you.
All right. Bye, everybody. Oh, and if you have questions, feel free to stick around. I'll be here.
Okay.